Okay, hello, my name is Jeff Schwartz. Welcome to the second of a multi-part series. We haven't quite determined how many of these there will be, but I estimate at least 6. Trying to do them in half-hour increments as we used to do them in 1 hour. Today we will be discussing how to take what we learned last time about perfmon and expand upon it by using certain dynamic management views and information that SQL provides about its internal operation. This should not be construed to mean trace, the SQL profiler trace with the GUI and all that. That's not what we're talking about here. And as the session number 1 was, this one will be recorded, so you can go back and have colleagues listen if you so choose. And to begin, the discussion about DMVs and DMFs is that they are designed to give you a window into what's going on inside the SQL Server. This is a quote from a Microsoft document I found, and I thought it gave a very good description of what is really happening inside this particular area. So they provide in general, I mean there are hundreds of them, they provide in general information about files being used, in what ways they're being used, what did SQL wait for in general as an overall category, which queries are the worst, what are the resources and events that are being waited for by current queries. So if you're having a long-running query that is seemingly taking too long, how do we figure out what that will, what's causing that, and how do we figure it out? And what some tips and optimizations suggested by SQL itself about how to handle the indices that are missing, or it thinks are missing. Today, of all those categories, and there are many more, today the only ones we'll discuss in the interest of time are the file-related and the overall SQL-related awaiting ones because of the time constraints. But however, it should be noted that this is a natural extension of the analysis we discussed in the previous session. There are 2 types of DMVs, DMFs. One is a pure function, or a view. One's a pure function. One needs parameters. The other one doesn't. That's about the only difference. And you can use them interchangeably. You can use them in cross-applies and some other things. So we'll allude to some of that later in the presentation. Right now, for the rest of this session and its subsequent sessions, most of the time when I use the term DMV, it could be a DMF or a DMV because it's just too hard to keep straight about which one is an F and V. Especially when you start to get using them, you just learn how to use them, and the distinction kind of goes away. So what we want to show you today is how to provide a significant amount of information regarding the system overall, the database, performance, and some of the inner workings of SQL Server. Some of the DMV, DMF categories are shown here in this list. The ones that we're probably most interested in most often are the ones that are index-related, OS-related, execution-related, and IO-related. As you can see, there are many others, especially if you're doing mirroring or something of that nature. You want to become familiar with those. But for most people, these are the ones that they will look at all the time, and they're very handy. So starting on 2005, the DMVs are the pretty easy ones to use. You pretty much run the query and see what it returns. There's not much else to it. Most of them, because they're all, what comes back are numbers, not names. They are required to be joined with other DMVs and sometimes DMFs to get exactly what to turn all those numbers into names that'll mean something to you. And so if you think about a query plan, for example, there's a lot of moving parts about the plan handle and different things. Those all have to be resolved by the query and things like that. So most contain values since the last SQL Server restart unless manually reset. And this is really great from a sampling point of view because we don't have to worry anymore about, well, we didn't sample for 30 seconds, and in that 30 seconds everything went crazy. Well, you didn't lose it. It's in there. It's in there. We caught it. And depending on the degree of frequency, you may have caught it a few times. So effectively, the takeaway here is that it's perfect for periodic or intermittent sampling because no data is lost by sampling. That is the key element of using this kind of data. And if your frequency is high enough, say 30 seconds or a minute, you will really not lose much of anything in terms of granularity and being able to zero in on a very small window to try to figure out what the heck happened in that special time. There are 3 DMVs that can be cleared out manually, but all the others cannot without restarting SQL. And of these, the one you would probably use the most often is the top one. And that's the one that clears out the overall category wait times for SQL. Why they don't allow us to clear some of the other ones, I don't know, but it would be handy to have more than just 3. Guidelines. Most of the performance DMVs that we use begin with sys.dm underscore. So if you want to find out all the sysdm views out there and functions, that's what you need to do. Just do just go ahead and grab all the views that are out there that start with sys.dm underscore. As I mentioned before, you have to reconcile numeric names with static values so that you can get text names that make sense to you. So instead of having table number 1, 2, 3, 4, 5, 6, it's personnel or something like that. It makes it much more consumable by you. Since most values are accumulated from the last restart, you can really vary the sample rates depending on what your goals are. So sometimes you can do this sample rate stuff range from 1 minute to a couple times a day. You aren't going to lose any data. If your data bumped greatly in the middle and then went back down, you won't see it if you do a very sparse collection. If you collect every minute, you'll probably get very close to what you were looking for. It's just a personal choice and how much overhead your system can tolerate. Systems that are tolerate a lot of these all the time under some conditions when they're super tight. The problem is that they do consume some resources. The resources are extremely light. But unfortunately, not everyone in management understands that, and therefore they don't want to try anything like this. So basically what you do is you collect samples and effectively just write them down. So it'd be kind of like filling a bin where you count and you see there's 100 in there, and then you come back and you count another 100 and another 100 and another 100, and so if you ever wanted to go back and look at what the differences were, in this particular example, you would have 100 each time. But that's what we're after here, is you have to calculate the differences between individual samples because the numbers constantly increase. And if you just use the raw numbers, then you go back to the time when SQL started, which for some of my customers has been several years. So this is something that you have to keep in mind. Um, make sure that when you're doing this diff operator, you're doing the difference with the same database ID, object ID, and index ID if applicable, or the file ID, database ID, file ID. The difference is that you have to match like things and make sure that you join the same database, the same file, the same everything all the way down to make sure you've got the right comparison, because you do have to subtract JSONs. I could tell you now that on 2014 they released a new function called lag, which makes this kind of work extremely simple and faster, and the code is much less convoluted. So I would recommend, if you happen to be using a 2004, grabbing some 2014 data, that you start looking into the lag function, because it came out on 2014. Okay, critical views required for converting numeric DMV and identifiers into understandable text. Here are some of the other, I won't call them, I guess they're views technically, but they're not the dynamic management views. They're standard system views that will give you what you need. Sys.databases will give you, the databases and the numbers and all that stuff. The partitions the same way. Configurations, OS sysinfo, so you can see you're getting information from other places. Now this is from system-wide on slide 7. On slide 8, this is for a database. So it'll show you the queries that ran against each database. And for those to decode them, we use sys.objects, sys.indices, sys.filegroups, and sys.database file names to get the physical file names. So you need to, things have changed a little bit. If you look at the note regarding sys.indexes, you'll see that it will do the connection, but it will not provide the row counts as the sysindexes old way does, which they're going to de-implement. But you can fill in the same information from sys.partitions. So once you've seen an example, I suggest you just hang on to it, and then you can use it to decode anything you want anywhere. It makes it very easy. Now, I should make a note that you don't have to record. You can record this information and also record the other information. You don't have to necessarily do some extremely complex queries to resolve all these things so they make a lot of sense. What I tend to do is write them down in their simplest form to a CSV file using SQL command, and then I come back later and join everybody up. So we've got two methods here. We've got method 1, which is capture before, so we take a snapshot effectively. We do our workload. We capture again for the after. We load the data into spreadsheets, and we do comparisons. So that's not too bad. Method 2 is a little bit more complex, and what it does is store every 1 to n minutes, stores it in a flat file, and then after everything is done, we load those into an off-site SQL table, or you could put it on a separate on-site SQL table, and then use SQL itself to do all the comparisons of the differences and all that stuff, and that's where that SQL 2000 and 2014 lag function comes in very handy. I think I misspoke before, and I said the lag came out on 14. I'm sorry, it came out on 12. So extract interval data and then you take that data and dump it into spreadsheets, and then you can graph it and do whatever you want with it. Now here's a specific view. This is the one that's used to grab all the I/O information for whatever levels of data you want. So it can get you all the log and data files for a specific database. It can get you all the log and data files for the entire system. It just depends on what you've asked for with some of the other parameters. it's ideal for determining what your most active files are and what your which files you were struggling on. I worked with a colleague yesterday, and she had a drive, a disk lun that was 100% busy all the time. And she wanted to know, this is from Perfmon, and she wanted to know what our next step was. And I said the next step is to try to grab some of this information and see which files are actually in trouble. Are all the files on D getting bombarded, or are just a few? And could those be moved anywhere so that all the files on this LUN D would, could do better? So you took some of the work off and moved them better. The null parameters give you the information about the files, and you specify the two parameters. If you say null, they will just return everything for the current. Basically everything is. Basically everything is. Basically everything is. Everything is returned. And the nice part about this view is that you can find out your most active files, the most active data and log files, the read-write ratios, IO sizes, all kinds of things. And so this is very helpful. The time series is extremely helpful when you're able to figure out, okay, well, during 10 to 11, this file was hit predominantly with a mountain of reading to get into a query or whatever it happened to be. So those are very helpful things like that. The other information that you can get out of this is the ID of the database. Again, you look at I talked earlier about reconciling these IDs. You get it, the database and file, but then also you get the number of reads and writes issued against that file, the number of milliseconds since it started, the total bytes read and written from, total time, as well as read writes specifically, and the number of disk bytes used by this file on disk. So it kind of gives you a very complete picture. In 2014, they added a new field called queuing, queued.io, but I haven't seen anything but zeros in those numbers yet in my testing. I just may not be testing it hard enough. Here is an example of what a spreadsheet looks like. I apologize that I've got two separate things going. Really, this is one linear spreadsheet that goes from K through N. But I just wanted to give you a feel for what you can do, how you can organize this, and you can see clearly that, K was ahead of D, but D, F, and G were all right there. So they were very even. In terms of response time, you had some really slow drives on those same ones, K, D, F, G. Those are the same ones that had a lot of trouble. And so that's not surprising. So if we want to attack LUNs and start juggling and figuring out why the times are so bad, this little query, this little table gives us the information we need to move forward and try to address some of the problems. Because clearly we've got some LUNs that are getting hit around 9 to 10 times harder than the others. Maybe there's room in the other ones to move to them. Here is another example. Excuse me. This one is by file. And so the last one was just by the LUN. This one gives it to us by LUN and file name. I provide the internal file name because sometimes the file name that's sitting on disk is a little different than the file name that SQL actually, that we think of, that short name and everything. So this will show you similar data, but by database file. And so you can see that the top 4 that are troublemakers in this case are all tempdb files. So since those are pretty easy to move, we should be able to move them anywhere we want and take care of this. So that'll be pretty great. So now pictorially, which is where this gets to be more powerful, you can see very clearly that D, F, and G had a lot of problems. These are average wait times in milliseconds, and you can see those should be down in the 20s and lower, or maybe at most 30, and here they are in the 2000s. So, and you can see that it was horrible during the period about 349 to 351, and then it got better and better and better, with a little spike at around 355, but then after that it calmed right down. And so when you go back and look at your work, like what work was this doing during those same periods? So this one was by LUN. This one was the same graph, only it's by database file. So which of these database files were actually getting hit? And you can see clearly the big red dotted line is a tempdb file. You can see the solid black line is another tempdb file. And you can see that all the way through we've got tempdb is creating a lot of the havoc. You don't see, you see a few of the other database in here, the WinPerf Data SQL guy, but all the big players, for the most part, are the tempdb. And that in and of itself is very handy, because maybe you went in there and thinking, well, I had to move everything off of those LUNs, and now maybe I just have to move tempdb, which is a lot easier to do. So this one gives you read wait times. I told you earlier that you can have read, write, or overall. So here I wanted to see what the values of reads were like. Were the high times always read, or could the writes have had some bearing on it? And as you can see, it's tempdb4 again. You can see that it's the WinPerf data file this time. And you can also see it's another WinPerf data file. Those 3 files are the ones that experienced the most stuff when they tried to read. When they tried to write, the pattern looks very similar to what it looked like before. So this thing is having trouble when it tries to write a lot. And then all these numbers get terrible. So to me, what this shows is that reading under normal conditions is pretty good. It's the writing that's getting messed up and slowed down, and you don't have the ability to get the writing through that's needed. So again, the conclusion that seems to be developing here is that we want to move tempdb somewhere else so that it's not applying this kind of pressure. This is another graph that you can use to figure out about the bytes transferred by file graph. So you can see here, if you're transferring a whole bunch of data, who's doing it. In this case, it's pretty even. You've got about 4 files there that are being evenly used, and you can see when their peaks are and as they move down. But this, again, gives you a lot better feeling for if you have to start moving things around. Most people look at space, and that's great. But then you also ought to look at something like this to be able to figure out, where do I move these guys, who's not only got the room, but who's got the ability to handle some of this, and which ones do I move? I probably take 2 of the big ones and put them somewhere else by themselves, or something like that, or with some low volume data. Now this graph is a little bit messy, but there's a reason for it. I wanted to show you that what the relationships were between utilizations and I/O times. And you can see in these particular cases, some of them are almost exact. And that's pretty important, that the utilization is skyrocketing, and so we have to be able to say, that this is what's causing the I/O times to get high. And the reason that that's important as well is if it were a shared LUN and some other system were clobbering this system, you wouldn't see necessarily the utilizations be so horrifically high when the response times were high. But in this case, it seems to be making its own issue. The disk may not be strong enough, but there may be, if we spread the wealth across the number of disks, we probably will be okay. And this is byte traffic. So this one's utilization and file weight. This one's how much work we're doing and how much waiting. And you can see, again, we have a lot of overlapping correlations here. You can see a lot of solids and dotted, right over the top of each other with some hardly any variation. So these, again, show us that the I/O wait times are a function of the volumes. So when the volumes get really high, like up to 100, up to a gig, then we need to figure out what we're doing and try to see if we can't move things around. Now again, because this is at 3 in the morning, we may not care, but if this were at 5:45, 6 o'clock in the morning, there could be a very good chance it could get longer as the database grew and make life very difficult for us. SQL Server operating system views, there are many of them. So there are 3 that we use the most: the OS wait, OS waiting tasks, and OS latch. OS wait is useful for diagnostic performance problems in large categories, like do we have too many parallel queries running on this system? Are we locking like crazy somewhere, et cetera, et cetera. There are 771 possible wait types as of 2014. These things seem to grow by a few hundred every release lately. Some of them are innocuous. They're just functions of daily operation. It doesn't matter. And you definitely want to release those from consideration when you, when you actually do your wait types and figure out that, oh, this one's just part of SQL's normal operation. When it's idling, that number is big, so we want to get rid of those. And those are documented in many different books. It's very useful to categorize what all the meanings are, especially when you're talking to management. Management is not going to know, typically, what an I/O completion is, what an async I/O completion, an async disk pool lock, a page I/O latch, DT, and any of that other stuff. They're not going to know what all that means. But they will know if it's saying you're getting tied up in I/O handling. The same applies to the latching category. The same applies to the parallelism category. So what I typically do is I provide 2 graphs, one that shows the graph as it would look with all of its specific wait times, and then I provide a summary of that when it's done. So here's the example with the full-blown, with the raw wait types. You can see CX packet in here, log buffer, I/O completion, async I/O network, page I/O latch, shared and update, and so on. Okay, now this is the same graph, just categorized, so that we now have fewer slices to worry about, and we still get the picture across. Parallelism, network, I/O, logging, latches. It makes it a lot cleaner to present that to management. The SQL Server wait times versus processor wait time. This is a handy graph because you can see when the I/O times, how the I/O wait times, the network I/O wait times and the parallelism I/O wait times all interact with processor wait time. Did the processors keep moving when all the problems occurred? Did the processor stop having work to do because things were so tied up in the disk subsystem? In this particular case, we see that the processor dropped, but not significantly, and it still had enough work to do and keep going while the other problems were developing. And that's very important as well. OS waiting tasks is very important because it helps you decode some of the query plans of active queries. It can be used to construct blocker waiter lists. It can be used to construct what's the current query running in the system right now that's running for 2 hours, what is it doing, and how do we get information out of it. So in there, they have things like the total wait time, name of a wait type, the task that's currently got it, blocking session, and what resource is being contended for. In this case, there are fewer latches, 163, but they can be most helpful when dealing with I/O subsystem performance issues or index overhead performance issues. Under extremely high volume insert events, you will see latching go way up, and it's not necessarily I/O latching. And that's this last point, and you just, there are certain thresholds that once you cross them, you start building up exponential queues in front of some of these numbers. The views return information about all latch types. We have the same problem we had before. We've got all these arcane names. What do they really mean? Where do they really fit? This gives you kind of a cheat sheet for some of the bigger ones. The first group goes into buffer. Second one goes into allocation. Third one goes into parallelism. And so those graphs are so much easier to understand if you do a buffer allocation and parallelism graph than trying to graph all these little components that went into it. So in conclusion, use DMV information to visually correlate system metrics with anecdotal user experiences. The nice thing is you won't be losing data, so you will catch it in there, depending on your frequency. Your frequency will only control how close you get to the problem. You get all kinds of great information about file usage. You'll see files on the same LUN that get dramatically different response times. Some will be perfect, and some will be horrible. And it's nice to be able to know that, because if you move one that has a great response time to another LUN, you probably won't see any change, and everyone will wonder why you were doing that. In the areas in general where SQL is I'd appreciate it if you'd attend session 3. I know these are very short and sweet, but I know people's time is precious, especially these days. So I'm trying to keep these to right around a half hour, and but give you enough to where you can go out and play with them. The next time I'm going to talk about how to, I talked in generalities about how to do the capture of DMV data in real time, and how we can then turn that into something that you can actually use, like in a benchmark situation or in a real-time situation where you're watching things all the time. And to take some of the data that we've got, we saw potential problems for sure on some of those graphs that, somebody needs to do something somewhere. And I would also appreciate it if you would complete the 4-question evaluation to let us know how we can help you and what other topics you would like us to cover in the future. And with that, I complete the webinar. If you have any questions, please feel free to post them to the moderator.